So, good evening, everyone. My name is Abhishek. I am going to cover the week 4 live interactive session for this week. And till now, we have already covered 3 weeks, and where we have discussed the basic thermodynamics. We have also discussed different relations, thermodynamic relations using Maxwell relations and other relations like Clausius-Clapeyron equations, entropy generation, entropy exergy destruction. So all these things we have already discussed. Till last class, we have already been discussing some of the thermodynamics, various things of thermodynamics. And this week we are going to discuss the basics of bit of reciprocating engines, or let us say it's a IC engine. We are talking about internal combustion engines. Okay, so if you have any doubt, like you can write a mail on this. So I will be happy to answer you. So last class, whatever queries you have sent, I will be answering it very soon. I was a bit occupied with my work in last week. And if you have missed some of your lectures, then you can find the recorded version of these lectures on this NPTEL channel. Now, before that, this week's we have already covered lecture number 11, 12, and 13. So, for that, what are the things that we have discussed? I will be discussing it in brief. So, this week we have started with the by taking that we have already discussed what is a Carnot engine. We have already discussed what is a Carnot engine, which is a completely reversible engine. And when we are talking about idle cycles, these although we are not telling it, these are completely reversible. Like there are two types of irreversibility. One is internal irreversibility, and one is external irreversibility, which has been discussed very and very vastly in the lectures covered by the instructor. Okay. Now, whenever we are not considering one of this, we are talking about the if there are no internal irreversibility engine, then there comes the idle cycles, which has a presence of external irreversibility. Now, external irreversibility is due to the temperature difference between existing between two bodies, which has a finite temperature difference. Now, what will happen if there is a temperature difference? If there is a temperature difference, there will be a heat transfer, which will cause the various forms of energy transfers. Okay. Now, in when we are talking about any reciprocating engine, there are various processes taking place which are not practically possible to identify. Okay, that is why what we do is we want to somehow replicate the actual cycles that are taking place in a reciprocating engine with by replacing it with some idle processes. Like for example, the suction process may not be constant pressure. It might be having other reversible irreversible things, like there is might be pressure drop, or there might be even energy heat transfer. But when we are talking about idle cycle, we don't consider all the irreversibilities. We neglect the internal irreversibility and try to identify the different performance parameters, and based on that, so that we can analyze what are the effects on a particular parameter. For example, if we increase the effect inlet pressure, now what is its effect on the energy efficiency of the engine? Because these idle cycles are nothing but the replica of the actual cycles. Now, from this we identify the important parameters, and based on that we decide what are the things we must take into consideration while operating on these actual cycles. Okay, so that is why these idle cycles are somewhat replicas of these actual cycles, and we can say that the highest efficiency is a Carnot efficiency in any case, which is vastly an theoretical cycle or theoretical engine. This has the highest efficiency. Then comes the actual, then comes the idle cycles, and then comes the actual cycles. Okay. Now, based on that, what are the things or different types of cycles that we have discussed till now were discussed in lecture number 12 and 13, out of which the first one is an Otto cycle, which is generally found in the petrol engine. Petrol engine or SI engine. Then the other cycle comes is the diesel cycle. As the name suggests, it is of used for the fuel diesel engine. Also known as CI engine. Now, when we are talking about the Otto cycle has also some of the disadvantages and also some things we have got in Otto cycle that are promising. So when we combine the both the advantages and the disadvantages of both Otto and cycle, we get an other cycle that is known as dual cycle, which will generally be a cycle which is existing between the Otto cycle and the diesel cycle. Okay, dual cycle. These are the modern day engines. Okay. Now, other than that, we have already discussed what are the things that we have discussed is Stirling engines, and Ericsson engines. Now, this type of engines are generally found out in the power cycles or whenever we are dealing with any huge reservoir, like for example, any heat recovery system or renewable thermal systems. There, this type of engines cycles are used. You can find more about this in Google when you do Stirling engines. You can find out the Stirling engines is also used in solar thermal power plants. Okay. Now, what are the processes that are involved? I think you might be knowing it properly, but just I will brief them. Like there are two isentropic processes, and two isobaric processes. Sorry, isochoric. Petrol engine is isochoric. Okay? Isochoric, constant volume processes. Okay. Now, when it comes to CI engine, the isentropic processes stays the same. In place of one of the isochoric process, that is the heat addition. Heat addition is done here using isobaric, where the pressure stays the constant. Isobaric process, and one is the isochoric, which is the heat rejection process. Okay. Now, as I said, the dual cycle is the processes also stays in between this Otto cycle and the diesel cycle, and in which the two isentropic processes stays the same. These isentropic processes are the processes where the volume expansion and contraction takes place. Then heat addition. The heat addition takes place through two processes. First one is isochoric. Part of it is isochoric heat addition. Isochoric heat addition. Then the second part is the isobaric heat addition. And then comes the heat rejection process, which is isochoric. Okay. Now the Stirling engines will be somewhat, it resembles to the Carnot cycle. Carnot cycle, where the two of these processes are two are isothermal, and two are isochoric. Okay. Now in place of two isochoric, here the two are isobaric. Okay. So these were all the things that were discussed in this week's and based on that, there were a few derivations done on how to identify the efficiency of these engines. Mostly, we discussed auto, diesel, and dual cycle, and after that, we also saw how different state points can be find out using assuming that these are air standard cycle and air is assumed as an ideal gas. We used all type of ideal gas equation to identify the state points, the temperature, pressure, and the volume. Based on that, finally we'll be finding out three four important things. What is the one is the thermal efficiency, another thing is the mean effective pressure, or maybe the specific volume. These are all the things that we'll be discussing, and we'll be also solving few numericals which will be helpful while understanding this type of cycles. Okay, so let's start then solving the numericals. Okay, so, okay. So can you see the screen? The first question is compression ratio of a reciprocating engine is defined as the ratio of, tell me.
Maximum to minimum volume, sir.
Correct. So this asks for any reciprocating engine, but for instance we can take an Otto cycle. If this is a P versus V curve. Otto cycles, let us say first 1 to 2 is isentropic compression, where we reach from volume 1 to volume 2. Then the constant volume heat addition. Then the isentropic expansion. Then finally the isochoric heat rejections. Okay. Now V1, this much is the VC, the clearance volume, and this part is Vs, the swept volume. Okay. And based on that, we can also say that this part is the, whenever we are talking about any engine, if the piston is the more the below as the most lowest point, that is the BDC, and when it is at the highest point, that is TDC, and this much volume is the clearance volume, and this has been discussed in the lecture as well. So the compression ratio is the ratio of the volume, the maximum volume, that is the volume at the VDC and the volume at the TDC. So it is V1 by V2. Okay. So we'll move ahead.
Okay, sir.
Yeah. Okay. So the next question is, an Otto cycle is characterized by what? We have just discussed this one.
So, yes, sir. Isochoric heat addition and isochoric heat rejection.
Correct. So I just drew the PV diagrams of the Otto cycle. This is the PV diagram of a Otto cycle. Now here there is compression, isentropic compression, where we will be providing work. Work will be done to the system. Done on the then comes the heat addition. 2 to 3 is the isochoric heat addition term, where here Q supply. Okay. Then comes the work will be given by the system, will be done by the system. There will be expansion, isentropic expansion done by the system. Okay, then finally heat will be rejected, and that is isoporic or constant volume heat rejection. Okay, this is all about the Otto cycle, and based on that the correct option is isoporic heat addition and isoporic heat rejection, the first one, option A. Okay, so we'll move to the next question. Yeah, so the thermal efficiency of an Otto cycle is, so if you remember just the thermal efficiency formula, you can directly answer from that.
Yes, sir. That is 1 minus 1 by compression ratio power gamma minus 1.
1 by RC, let us say compression ratio is
RC.
RC, yeah, gamma minus 1 by gamma. Okay,
Yes.
so now tell me what is the relation for example, if you are increasing RC, what will happen to the efficiency of the Otto cycle?
Efficiency also increases.
Correct. So efficiency will increase as this is in the denominator side. The whole, this whole term with increase of RC will reduce, and that will that will increase the efficiency of the Otto cycle. Now what happens if we increase the gamma? Will it?
Yes, sir. Gamma for a monoatomic gas like 1.67.
Yeah.
Eh,
So absolutely right. So already a graph was discussed, a plot where it is talking about x-axis has the RC and the y-axis has efficiency. Now RC cannot come below 1, so this is the curve, that was discussed. Okay, now along this gamma increases. This is, as you said, this is for gamma is equal to 1.66, that is monoatomic gas. This is 1.4 and this is 1.3. Okay, so as the gamma increases, the efficiency of the Otto cycle will increase and as the RC increases, the efficiency of the Otto cycle will increase, but based due to some constraints we cannot go beyond a certain amount of RC. We cannot increase the we cannot increase the compression ratio. Okay, that is one of the drawback, and based on that only we switch to diesel cycle. Okay, so the correct option is directly proportional to both compression ratio and the ratio of the specific heat, that is gamma. Okay. Question number 4, just now we discussed an Ericsson cycle comprises of what?
Two isothermal and two isobaric processes.
Correct. So 2 isothermal and 2 isobaric processes I have already discussed, and you can refer to lecture number 13 to understand more about it. Now coming to solving few numericals, let's start with this question number 5. An engine running on Otto cycle receives air at 85 kilopascal, 280 Kelvin, with the maximum cycle pressure and temperature as 5 megapascal and 2000 Kelvin respectively. The temperature at the end of expansion cycle is dash Kelvin. So try to solve this question, and then we can discuss what are the what is the value that you got.
In this problem, shall I take P2 pressure after compression? The P2 which is equal to square root of P1 P3. For Otto cycle, whether it is applicable, sir?
That is,
After
see, that can only be applicable when the condition is that first of all you are talking about when there is a maximum compression work. I think that is used in a compressor, that formula, root over a P1 and P3. Okay. Okay, so here you can't use that this formula because no such consideration has been made or has been mentioned in the question. So you have to start by thinking by using all the how to use the state points. What are the state points? Whenever such question is given, consider what are the state points that has been provided and what are the information that I can derive from this question. And the third thing is based on that, what are the missing state points that I need to find out. After that, you can find out the efficiency or whatever it is asking. Okay. So just go step by step, you will be able to answer this question.
Here P1, T1, P3, T3 is available, sir.
Correct. And what it is asking?
T4, sir.
Correct. So you have particularly the state points of 1 and 3 available and 2 and 4 are missing. And how do you find that?
Respect to pressure, volume, temperature correlation
Correct.
between 1 and 2. Yes.
Correct. Just go for it.
If I am trying with P1 V1 power gamma equal to P2 V2 power gamma, here also two unknowns are there. T2 by T1 equal to P2 by P1 power gamma minus 1 by gamma. So here also T2 P2 not available.
Okay.
If I am trying to use T2 by T1 equal to V1 by V2 power gamma minus 1, here I don't have compression ratio.
Okay.
That is also not possible.
Okay. Okay then. I will solve then this question. So what are the hints we have to find out? First of all, as I said, draw the curve. Either whatever you are comfortable with, whether it's P versus V or T versus S. Okay. So at 1, at state point 1, P1 is equal to 85 kilopascal, T1 is equal to 280 Kelvin. These are the things that I has given. At state point 3, P3 is equal to 5 megapascal or 5000 kilopascal. T3 is equal to 2000 Kelvin. Okay. It is asking what is the unknown. It is asking what is T4. Okay. Now, one of the things that you might have skipped, one of the other hint that is given that you might have skipped is the Otto cycle. This term. Now, what does Otto cycle means? That means V2 is equal to V3. This gives a relation, very important relation, that is P2 by T2 is equal to P3 by T3. Similarly, V3, V4 is equal to V1. So P4 by T4 is equal to P3 by, sorry, P1 by T1. Okay. Now let's find what is T2. Now T2 is equal to, we'll use the adiabatic equation, PV to the power gamma is equal to constant. If you cannot remember the equation, just remember PV to the power gamma is equal to constant. Based on, now replace P with V with respect to T and P relation, T by P to the power gamma is equal to constant. Now T to the power gamma by P to the power gamma minus 1 is equal to constant. So that implies T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma. So T2 will be T1 is equal to P2 by P1 gamma minus 1 by gamma. Now in this case, we don't know what is T2, we also don't know what is P2. Okay, that's all, that's fine. But what we know is T1 and P1. Now coming to the next equation, that is P2 by T2 is equal to P3 by T3. So in place of P2, just write P2, and in place of T2, just replace this equation, T1 T to the power P1 gamma minus 1 by gamma is equal to P3. Do we have P3? Yes, we have P3. It is 5000. And then what is T3? T3 is 2000 kilo Kelvin. So always whenever you are using any ideal gas equations or this adiabatic equation, almost every time try to keep temperature in Kelvin. So in this case, what is the unknown now? We don't know P2. That's fine. Do we know T1? Yes, we do. We do know T1. T1 is 280 Kelvin. Do we know P1? Yes, we do know P1, 85 kilopascal. And same P2 we don't know. Okay. Now can you find out what is P2 then? Find out P2 in kilopascal. Did you get? I think now you
Yes,
will be
sir.
able to solve.
Yes, sir.
Just, yes, find out. So I am getting P2 is equal to 1626.93 kilopascal. Just check. Are you calculating?
Yes, sir. Yes. Yes, sir. Answer is correct, sir. Correct only. 1626.933.
Correct. So the next relationship that we need to use is always we know that whenever we are dealing with Otto cycle, we are dealing with two volume limit. Okay, that is V3 and V4 or V2 and V2 V1. So that means can we write what I will write? So okay, not going by that process. We can write by uh, P3, sorry, T3 by T2. Just I'm trying to make it more easier. T3 by T2 is equal to T4 by T1. Can we write like this? Mm, Okay, let's not go like that. Just directly now, can you find the what is the compression ratio now? Is V1 by V2, also known as P2 by
Now,
P1.
now
Sorry.
Now T2 first of all shall we find, sir? T2 equal to T1 already known.
Yeah,
T2 just now we have calculated.
yeah, find out the same thing only. You just need to know what is P2 by P1. P2 by P1 is equal to 1, V1 by V2 is equal to P2 by P1, 1 by gamma. So that will give you the RC.
Now T2 911.88.
Okay, what is the this thing you got? 8.23. I am getting the compression ratio. So 8.23 to the power zero point 0.4 divided by 1.4 into T1 is 280. So what are you getting as R3? Just tell me. Oh, sorry, RC. RC, what are you getting? Compression ratio.
Doing it, sir.
I'm getting 511 as T2. Just check.
Sir, I'm getting some kind of huge value. V1 by V2 is around 19.14. Whether it is logically correct, sir? No, compression ratio
P2.
up to 9.
No, what is the value of P2 you got? It is 1626, right? 1626.93, correct?
No, sir. 911. I have. Okay, sir. I will. I did a mistake. I correct myself.
Yeah, yeah, just correct it. I'm still getting 8.235 as the RC.
T2 around 651, sir.
T2. RC, you are getting
Uh,
this one, right? 8.23.
uh,
Okay. Okay, I got it. What mistake I did? It is, I think, gamma by gamma minus 1, right? When we are talking about.
yes. Yes, sir. Now compression ratio is around 8.235 R
Okay.
value.
Okay. 8.23, right? Okay. Then
Correctly, sir.
T2 is 280 Kelvin. Okay. 8.23 to the power. Four divided by 1.4. I somehow getting 511.33 Kelvin. I think I'm doing some mistake. Okay. Okay. What mistake I am doing? I'm just okay. This mistake you also take care. I think this is a very silly mistake that you can also do. So P2, I was putting that P2 by P1 is 8.235. It is not that. So P2 by P1 to the power 1 by gamma is 8.235. So just we have to do 8.235 to the power zero point 0.4 into 280. We'll get 650.76, correct? This is what you are getting.
Yes, sir. T2 correct.
Yeah.
650.
So once T2 is done, can you find out T4? We know that
Yes.
the
Yes.
compression ratio and expansion ratio will be same. So that will give us that V2 by V1, V2 by V1 will be equal to V3 by V4. Okay.
T4 is around, I'm getting 860.5, sir.
Yeah. So
Yes.
based on that, if you put your formulas, like you have T3, you have T3, from T3 you can find out T4 through the relation. I think T3 by RC to the power gamma to the power gamma. You will get gamma minus 1. Will get the value T4. So T3 is 2000 divided by 8.23 to the power zero point 0.4. 60. I'm getting T4 as 861, 860.7, 860.1 Kelvin. Okay. Are you also getting this value?
Yes, sir. Yes, sir. 860.5. Yes.
Okay. Okay. So this is how we solve it. Just go step by step. Okay. Now question number 6. A gasoline engine with a compression ratio of 10 receives air at 50 kilopascal, 280 Kelvin. Temperature at the expansion stroke is 750 Kelvin. If air can be assumed to be ideal gas, if air can be assumed to be ideal gas, with R is equal to 0.287, the mean effective pressure of this cycle. I think you can give it a try.
As per the mean effective pressure definition, that is equal to work done divided by
Yes,
V,
net work done.
V1 minus V2. Net work done
Yeah, net
divided
work
by
done. Not only work done, net work done, because
net work done.
correct, by Vs, or you can
Yes.
write W net
V1 minus V2.
V1 minus V2. This is the swept volume. Okay.
Here heat supplied minus heat rejected. CV into T3 minus T2 for finding the heat supply. In the meantime, heat rejected CV into T4 minus T1. We need to find the salient point
Yeah,
state
yeah,
points.
yeah. Let's go for it.
T2 temperature is 703.3.
T2. Okay. I have not solved this question. You solve it, then we can check.
problem. I have calculated the T2, T3, T4 heat supplied, heat rejected, and all, sir. Shall I use that for finding the V1 specific volume at state 1?
Hmm.
P1 by RT1. Shall I
Yeah,
the
use this
specific
one.
volume?
So, okay, so let me start to solve this question. So first of all, what are the state point? As I said, what are the state point that are given? We'll see. So at 1, we have P1 is equal to 50 kilopascal, T1 is equal to 280 Kelvin, and RC is given 10. Now the temperature at the expansion stroke is 750 Kelvin. So that is given as at 4. At the expansion stroke, okay. So expansion stroke means it's T4, 750 Kelvin. Were you able to identify this? Temperature at the expansion stroke is 750 Kelvin. This is T4, okay.
Yes, sir.
If air can be assumed to be an ideal gas, okay, the mean effective pressure. So of course we have to find out all the points. So first we'll start with T2 at point 2. Now at 2, what are the things we don't have? Okay, we don't have T2. So let us find out T2. T2 is equal to T1 RC to the power gamma minus 1 by gamma. Sorry, RC
No,
to
sir.
the power
Gamma,
gamma.
gamma minus 1.
Correct.
Yes,
So RC to the power gamma minus 1. So T1 is equal to T1 is given
700.
280 Kelvin. So RC is 10 to the power 0.4, and you will get as 0.4 into 280. So I'm getting 703.33. Okay. Were you also getting this one?
Yes, sir. Yes, sir.
Okay.
Same values.
So the other thing is P2. How do we find out P2? It is P1 to the power P1 into RC. RC is V1 by V2, and we'll do P2 by P1 is equal to V1 by V2 to the power gamma. Okay, find out P1.
1255.94 kilopascal.
Yeah, 1000. I'm also getting 1255.94 kilopascal. So based on the information we calculated what are the state points for at 2. And one more thing also we can calculate now itself, it is V1. What is V1? It is the specific volume at the state point 1. We can calculate by RT1 by P1, where R is equal to, it's not the universal gas constant, it is R by M, universal gas constant by the mass, molecular mass of air, which will give, which is given that 0.287. It is just the gas constant. So 0.287 into T1, T1 is 280 Kelvin, by P1, P1 is 50 kilopascal,
1.6072 meter cube per kg. 1.6072, sir.
so 1.6072, let us take it as 1.61 meter cube per kg, and from here can you calculate V2? Of course you can do. So it is 0.16 meter cube per kg. Okay, now if you see the effective mean pressure is W net by V swept, that is V1 minus V2. So V1 we have, V2 we have, we need to find out W net. So W net, one of the easiest way to find out is find out efficiency, because this is an Otto cycle. So efficiency is 1 minus 1 by RC to the power gamma minus 1, okay, by gamma. You have this one. This is also equal to W net by Q in is equal to whatever ratio you get from here. Just multiply W Q in, you will get what is W net. This is one of the easiest way, but for Q in, you need to have T3 and T2 point. So from here T3 we don't know, T2 we know. So from here, can we calculate T3, or we have T4? Can we calculate T3 like the last step?
Yes, sir. T4 by T3, which is equal to V3 by V4 power gamma minus 1.
Is V4 by V3 or V3 by V4?
V3 by V4, sir.
Correct.
Because I have taken T4 by T3.
Okay.
That's why T4 by T3, which is equal to V3 by V4 power gamma minus 1. If you are substituting the compression ratio value, T3, which is equal to 108, 1883.9 Kelvin. T3, which is equal to 1883.9.
Okay. From here I will find out T3. So it is 10 to the power 0.4. Sorry. I'm getting 1883. Are you getting that one?
Yes, sir. Correct, sir. 1883.9. Yes.
Okay. So that is done. So now we can find out what is the efficiency. Calculate what is the efficiency of the Otto cycle.
Efficiency around 48.2%. That is 0.482.
Correct. Because 1, okay, minus plus 1 is 48.2% or 0.482. So now find out what is W net. 0.482 into CV T3 minus T2. So CV is 0.718. 0.718 into T3 is 1883.91 minus T2 703.33 into 0.482. It's 408.57. Are you getting this value?
Yes, sir.
408.56
kilojoule
per kg. Okay.
Yes,
now this one is done. Now just find out what is mean effective pressure. It is 408.57 divided by V1 minus V2, which is 1.61 minus 0.16. I am getting 283.72.
Yes, sir. 281.96 I am getting. Okay.
Okay. So yes, this is how this question is solved. Did you get it?
Yes, sir. Same. Okay.
Now coming to the next question. An Otto cycle with a compression ratio of 10 receives air at 290 Kelvin and 85 kilopascal. If the peak pressure is 6000 kilopascal and its highest temperature. Almost similar question. Try to solve it, then I will solve. First step, draw the.
Okay, sir.
Yeah. First step, draw the curve. I am comfortable with PV curve, so whatever you are comfortable with, just draw that.
Sir, T3 maximum temperature I am getting around 2047 Kelvin, sir. 2047, 2047 Kelvin.
Okay,
Mm.
let's see. So an Otto cycle with a compression ratio of 10. So things that are given are compression ratio is 10, receives air at, so P1 is equal to 290, 85 kilopascal. T1 is 290 kilopascal, 290 Kelvin. The peak pressure is 6000 kilopascal. So in an Otto cycle, where is the peak pressure? The peak pressure that where we see it, it is at 3, at state point 3. So at P3, it is saying 6000 kilopascal. So it's the same question. So we have some of the salient features or the state points missing. So let's start with finding out what is. We need to find out the T3. Okay. So start with finding out T2. So T2 is, we have already developed this formula, is RC to the power gamma minus 1. So T1 is 290 Kelvin, RC is 10 to the power 0.4. If it is possible, try to remember, mostly whenever you will get any question, it is mostly you will get in an Otto cycle the compression ratio is 10. So better to remember what is 10 to the power 0.4, then your calculation will be really fast. So it is around 2.5, 2.51, or you can just remember 2.5. So into 290, I am getting 728, 728.44 Kelvin, correct? Now once T2 is done, we need to find out T3. So it is constant volume process. So T3 by T2 is equal to P3 by P2. Do we have P2? We don't know P2. Now how to find out P2? P2 is P1 into P2 by P1 is equal to V1 by V2 to the power gamma. So V1 by V2 is RC. So P2 is equal to P1 into RC to the power gamma. So P1 is 85 into 10 to the power 1.4.
2135.1 kilopascal.
So 85 is 2135.1 kilopascal. So now just put that formula, 21351 by P2, sorry, P3 is
Sorry, sir.
yeah,
6,000, sir.
yeah. So it is 6000 by 2135.1. T3 we don't know, T2 we have calculated as 728.44. From here, if we calculate T3, we are getting I'm guessing getting 2047. 0.03 Kelvin, which you have also got. Okay.
Okay, sir.
Now coming to the next question. A diesel cycle has a compression ratio of 20. Now we are going to the diesel cycle. Has a compression ratio of 20 with an inlet state of 95 kilopascal, 290 Kelvin, and a maximum cycle temperature of 1800 Kelvin. If air can be assumed to be an ideal gas with R is equal to this one and CV is equal to this, the net specific work output. So it is asking W net specific. So in any of such questions, the first step is to draw the diagram PV. So the it is our diesel cycle. So constant pressure heat addition 1 to 2, 3, 4. This is the heat addition process. Okay, from here, what are the things that are given? Given are compression ratio RC is equal to 20, which is V1 by V2, with an inlet state of Inlet state is given, so state point 1, (95 kilopascal), P1, T1 is equal to 290 Kelvin, and a maximum cycle temperature. So where do you think the maximum temperature will be observed?
T3, sir.
Correct. Because heat addition is taking place there, so it will be 1800 Kelvin. Now, if air can be assumed to be an ideal gas with R is equal to 0.287, R is equal to 0.287, it is given. Okay, these are all we know it. CV is equal to 0.718 or 7, it is given. Fine. The net specific work output. So, W net we have to find out. Okay. If the cutoff ratio would have been given, then it would have become very easy for us, because we have T3, we would have find out T2, then directly T3 minus T2 into CP if would have done, then we would have got Q in, and if we had multiplied that, then the net specific work output would have been seen, can be found out. As it is not given, so we need to find out Q rejected as well. So find out. This is a bit lengthier question. Try to find out. Even we can.
Yes, sir. Trying, sir.
Start with T2, T1, RC to the power gamma minus 1.
I'm getting around 549.15 kilojoule per kilogram, sir.
Okay,
Uh,
we'll see that. So can we calculate what is beta or the cutoff ratio from here? V3 by V2 is equal to T3 by T2. Can we do that? If that we are able to do that, it is very easy.
cutoff ratio is around 1.87.
See, V3 is 1800 divided by 961. The T2 is correct, right?
T2 is around 961.2.
Correct,
Sir, correct
correct.
only, sir.
So
1.87.
we are getting beta is 1.87. So can we find out efficiency directly? Just I'm thinking like that. 1 minus 1 by, what is the formula? RC to the power gamma minus 1 then beta to the power gamma minus 1 by beta minus 1 into gamma. Am I right?
Yes, sir. Correct, sir.
Okay, so based on that, what is the efficiency we are getting? Just we'll find out. 1.87 to the power 4.
Around 65.27, 0.6527.
Okay, I'm just how much are you getting? 65. Just
Yes, sir.
20.
0.6527.
Was 87 power 1.87. Yeah, I'm getting somewhat like 65, 66%. 0.65. You are saying 0.65, right?
Yes, sir.
Now from here, calculate W net. 0.65 into 842.16. It's 547. Okay.
Okay, sir.
Then we'll go to the next question. A diesel engine receives air before compression at 280 Kelvin and 85 kilopascal. The highest temperature and the pressure the cycle are 2200 Kelvin and 6 megapascal. If air can be assumed to an ideal gas with R is equal to 0.287 and CV is equal to this mean effective pressure of the cycle. So almost similar question, just try it. Try to solve it fast. I will just tell the approach.
Okay, sir.
Are you solving?
Yes, sir. Yes, sir. For this problem, beta, I'm getting around 2.34, sir. Whether it is logical answer, sir. Beta
Yeah, might be.
2.34.
Yeah, no problem. You can go ahead. So here it is given that before compression, so that is P1. P1 is 85 kilopascal. T1 is 280 Kelvin. The highest temperature and the pressure are, so of course it is P3 and T3. 6 megapascal, 6000 kilopascal, and 2200 Kelvin. If the air can be assumed to be an ideal gas with R is equal to this and this, the mean effective pressure. Okay. Now for that, do we have bit compression ratio? Compression ratio is not given. For that, we need to find out T3, T2.
Compression ratio
So
is
is
around
T2.
21.
Yeah. So it is not given, but we are already given P3. So in a diesel cycle, this is the another hint. So in a diesel cycle, P2 is equal to P3, which is 6000 kilopascal. So V1 by V2 is equal to RC is equal to V1 by V2 is equal to P2 by P1 to the power 1 by gamma. So that is P2 is 6000 by P1 is 85 to the power 1 by 1.4. Twenty 20.91 I'm getting. So you are also getting 21. Okay. Now next thing is, can we find out beta? Beta is V3 by V2 or T3 by T2. So we need to find out T2. So T2 is T1 to the power P2 by P1 to the power gamma minus 1 by gamma. So P2 is 6000 divided by 85 to the power gamma minus 1 by gamma divided by 1.4 into T1. T1 is 280 is 944. I'm getting 944.86 Kelvin T2. Am I right?
Correct one, sir.
944.86. So inverse into 2200 is 2.3233. 2.33 beta. So can we find out the efficiency now? 1 minus 1 by RC to the power gamma minus 1 beta to the power gamma minus 1 by beta minus 1, another ratio of 1 by gamma. What is the efficiency you are getting? What is the efficiency you are getting? I am getting I'm getting 63.9596%. Are you getting this value?
Yes, you can
Huh?
I did a mistake, sir. I am correcting this.
Okay.
Yes, sir. 63.92.
Yeah. Now find out Q in. I'm getting 2160.1.
Heat supplied, sir.
Hmm?
Uh,
Sorry,
heat supplied around 1060.
how much you are getting? 2160, right? Your voice is not audible.
676.6, sir.
Okay, so I did some mistake. So R T3 minus T2. So T3 is 2200 minus 944.86
Okay.
into CP. CP, what is the value of CP? You have done CV or CP?
CP only, sir. CP only.
But the difference between T3 and T2, how much is T3 minus T2?
Sir, T3 minus T2 into 1.005. Heat
How
supply
it is
alone, I am getting 12,261.
correct. So what is CP value you are getting? Find out CP value. CP minus CV is R, right?
Yes, sir. Sir.
Uh, so what R is
1.0.
0.287.
Yes, sir.
CP is CV is given 0.717.
1.004. 1.004, sir.
1.004.
Yes, sir.
Okay, 1.004 into 2200 minus 944.86. It is 1260,
2000.
right?
1260. 1260,
Okay,
correct, sir.
okay. 1260.16 into 0.6396. It's 805.
Yes, sir. 805.24 kilojoule per kilogram. Yes.
Yes. Then find out W net by V1 minus V2. What is V1? MRT by T1.
Point 945. 0.945.
0.945, correct. 0.945 meter cube per kg. V2 is 0.0945. Sorry, V2 is how much? 20 we are getting. Sorry, I just took it as 10. Yeah, so 20.94. It is 0.045. Am I right?
Yes.
Yeah.
Correct, sir. Correct. Percentage is 21 we are getting, sir. So anyway, I have used that correlation P1 V1 power 1.4 equal to P2 V2 power 1.4. From this, already I calculated the specific volume at the state 2.045.
Okay. 2805.99. So I think you'll be getting 895.69 kilopascal.
Is 894.7, sir. 894.7
Okay.
kilopascal.
Yeah. So such question we have already solved. So we'll go to the next question. This is a question on the dual cycle. A cycle working on ideal dual combustion cycle receives two-thirds of the total heat supply at constant volume and the rest at constant pressure. It has a compression ratio of 9. State state at the beginning of the compression 90 kilopascal and 20 degrees Celsius, and it receives 2100 kilojoule of heat per kg of the working fluid. If air can be assumed to be an ideal gas with R is equal to 0.27 and CV 0.017, the thermal efficiency of the cycle is. So I think if the formula you can remember for dual cycle, that makes very easy. But as that formula is little lengthier formula, so remembering it is difficult. So you can directly go with the same process that we have been following till now. Just find out all the required state points. Sorry. This is 1, this is 2, this is 3, this is 4, this is 5. Okay.
Yes, sir. Here, heat supply takes place by in isochoric as well as isobaric
Correct.
process.
Correct.
Total heat supplied is 2100 kilojoule per kilogram.
KG.
2 by third is heat supplied during constant volume process, that is
Okay.
around 1400 kilojoule per kilogram.
Correct.
The remaining 700 kilojoule per kilogram heat is supplied through constant pressure process. So now in the same way, here finding T2, T3, T4, and then heat supply, heat rejected, and divided by heat. In this manner, I have tried
Yeah.
efficiency of dual cycle, which is equal to work done divided by heat supply.
Correct.
Instead of memorizing that formula, I have approached like this.
Yeah.
But I am getting the answer T3 and T4 and all 3000 something. I am getting, sir. Whether it is a logical answer, sir.
Yeah. Might
So
be. Might be. That can be
oh,
possible. That can be
yes, sir.
possible.
Yes, sir.
Yeah. If you have not done any mistake, then don't. On the calculation part, then this value is possible. Okay.
Yes, sir. But
So
logical thermal efficiency value is around 57.81. I have obtained, sir.
57, right?
It 57.8. Yes.
Yeah. If you see that like that, almost we have got some questions like auto cycle, diesel cycle efficiency is somewhat around 65%. We have got this in few questions, and auto cycles efficiency is coming around 50% or 48%. So if it is falling between these two, it is somewhat logical only. Okay, this is dual.
Okay, sir.
So for the before that, just I will again tell you how to solve this question. So cycle working on an ideal dual combustion cycle receives two-thirds of the total heat supplied at a constant volume. So based on that, we have find out what is the QV and what is QP. Now why we are doing that? So that we'll be able to find out the T3 and T4. That is the main purpose of giving this value. Okay. So the compression ratio is 9. So similar to the earlier question, T2 is equal to T1 RC to the power gamma minus 1. So T1 is how much it is given? It is 20 degrees Celsius. Remember it to convert it into Kelvin, 293. RC is 9 to the power 0.4. So 293 to the power 0.4.
705.6.
is I'm getting 705.6. Okay. Once T2 is done, then we need to find out T3. How to find out T3? It is CV into T3 minus T2 is equal to 1400. We have CV, so find out T3 from here. 1400 divided by 0.717 plus T2
around
705.6
2658.
2658.18 Kelvin. Now find out T4. So this find out T4, that is Cp T4 minus T3 is equal to 700. So 700 divided by 1.004 plus T3 is 2658. 2658.18. I'm getting 3355.
55. Correct, sir.
3355.39 Kelvin. Now, once all these things are done, find out what is T5. Can you find out T5? Is it required or it's not required? Yeah, it's Q rejected. You need to find out. For that, find out T5. So for that, you need to find out the expansion ratio. So what is T3 by, sorry, what is V3 by V5? Can we write it as okay? Just I want to develop a relation between RC, compression ratio beta, and RE is the expansion ratio. So RE is V5 by V4. In place of V5, can you write V1? We can write that. In place of V4, keep it same as V4. Multiply here by V3, V2, and this is V2. In place of V2, can you write V3? We can do that because it is a constant volume heat addition. So V1 by V2 is RC, V3 by V4 is 1 by beta, and V5 by V4 is RE. So RE is equal to RC by beta. Correct?
Yes.
So RC is given how much? We have 9. How much is beta? RC is 9. How much is beta? T3, T4 by T3. Just find out T4 by T3. 3355.39 divided by 2658.18. It's 1.26. So 9 divided by 1.26 is 7.12. Okay, so RE is that one. So T4 divided by 7.12 to the power gamma minus 1 is 0.4 to the power 0.4 inverse into what is T4? 3355.39. I am getting 1529. How about you?
Yes, sir. 1528.5. Yes, sir.
Correct. Okay. Now Q rejected is CV into 1529.35. What is the initial temperature? What is given is 293.
3.
Yeah. So minus 293
Around 8.
1717. 886.4647
Yes. Yes.
is kilojoule per kg. So Q rejected is done. Just subtract this from the 2100 divided by 2100. So efficiency is getting somewhat around 57.78%. Correct?
Yes, sir.
Okay. So these are all the types of questions that has been discussed. Now we'll go solve 2 3 more types of numericals, out of which I think one is only the new type. Let's see. So 11, question number 11, a gas engine operating on the ideal Otto cycle has a compression ratio of 6:1. So RC is given 6:1. The pressure and the temperature at the commencement of the compression, that is at the beginning of the compression. So P1 is 1 bar, T1 is 300 Kelvin. Heat added during constant volume combustion process. So QS, so it's only Otto cycle. So the total heat addition is 1170 kilojoule per kg. You determine the peak pressure, temperature, work output per kg, and air standard efficiency. Of course, this type of question we have already done. Just I will again walk through that, the approach. Solve this question yourself. Okay, 1, 2, 3, 4. Just draw the curve. Now we have to find out P2. So how to find out P2? P2 is nothing but P1 RC to the power gamma. Okay, we will get P2. Once P2 is done, we will find out T2. Do we need T2? No, we don't need to find out T. Yeah, I think we need to find out T2. So from here, find out T1 into RC to the power gamma minus 1. So T1 is given how much? 300 Kelvin. RC is 6 to the power 0.4. I think 6 to the power 0.4 is okay. 300 is somewhat around 614.3 Kelvin. Now once that is done, Cv into T3 minus T2 is equal to 1170 kilojoule per kg. Now find out T3. From here you can find out T3. It is somewhat around
2246 Kelvin, sir.
1170 divided by 0.717 plus 614.3. 2246, right?
Yes, sir.
So T3 is
Yes,
done.
sir.
Now once T3 is done, we know this is an Otto cycle constant volume heat addition. So it is P3 by P2 is equal to T3 by T2. From here find out P3. So T3 we have got, T2 we have got 614.3, and P2 we have got how much? 1 bar it is given. So 1 bar is 10 to 5 Pascal. So it is 100 kilopascal. 100 into RC is 6 to the power 1.4.
T4 around 1097. 1097, sir. 1097. Heat for finding heat rejection it is required.
How much you are getting P3?
T3 maximum temperature 2246, sir. That is correct. T4 is 1097.
That is okay, but you just tell me what how much you are getting P3.
That is
Peak
already calculated 2246.1.
P3
2246
peak pressure.
peak pressure.
P2 I am getting 1228 kilopascal, 1228.6 kilopascal into T3. T3 is 2246.1 divided by T2 is 614.3 is 4492, 4492.21 kilopascal. So peak pressure is done, peak pressure is done, peak temperature is done, work output. So efficiency is a direct formula 1 minus 1 by RC to the power gamma minus 1. Find out efficiency. From there you have already have work of W net efficiency into efficiency of the auto cell into W net.
Efficiency around 0.5116.
Yeah, somewhat around that only you will get. Okay, so once that is done, I think this type of questions we have already done. So question number 12, I think this is somewhat a new type of question. Determine the ideal efficiency of the diesel engine having a cylinder with bore. So bore means the diameter of the cylinder, piston, mostly the cylinder in which the piston is reciprocating. It's 250 mm. Stroke, the total length in which it travels is 350, 375 mm. And a clearance volume is 1500 cc with the fuel cutoff occurring at 5% of the stroke. Okay, 5% of the stroke. So stroke is Vs is V1 minus V2. Okay, find out first stroke volume. Vs is equal to pi by 4 d square into L. So pi by 4 convert into cc, that will be easier for you. So 25 into 37.5. What? You want to say something?
No, sir. Doing it, sir. Doing it.
So it is 25 whole square into 37.5 into 0.785. I think you will get 18,398. Calculate how much you are getting.
Sir, 18,407.
Okay, I think pi by 4, little bit of variation due to pi by 4. That's okay. So V1 is equal to Vs plus V2. So Vs is 18,398.44 plus V2 is 1500. As I've already said, V2 is the clearance volume plus 1500 is 19843 cc. Now, best way to solve this question is using a graph that will really simplify, but the expression that is being developed from this question, try to remember that that will help you to find out like there might be some questions in some competitive exams where you don't have the time to develop this equation. So remember that equation for solving. So it is PV, it is somewhat like this, this, 1, 2, 3, 4. So it is saying that the fuel cutoff occurring at 5% of the stove. So fuel occurring is at here. Heat addition is taking place at here because the compression has ended here. Now air is at its maximum temperature. Sorry, at its at least at is a temperature at which whenever the fuel will be introduced, the fuel will be introduced, there will be combustion and heat addition will be taking place. So, and the fuel cutoff will take place at V3. So it is normally it is saying that V3 minus V2 is equal to 5% of the stroke. What is the stroke? V1 minus V2. Okay. Now V3, just divide V2 on both the sides. So V3 by V2 minus 1 is equal to 5%, 0.05 V1 minus V2. So V1 by V2 minus 1. Okay. Now V3 by V2 is equal to 0.05. This is nothing but the RC minus 1 plus 1. So this is the equation you need to remember. Okay. What is the formula for beta? It is x% of RC minus 1 plus overall 1. Okay. Try to remember this formula, might be helpful. So now find out what is beta in this case. So 0.05. 0.05 into RC minus gamma.
Compression ratio itself, I am getting around 13.27.
Cutoff ratio.
No, sir. Compression ratio.
Okay, okay. So RC is
13.27.
okay. Just let me calculate. So BS is 18,398. Sorry, V1 is 19,898.43 divided by it's V1. V2 is how much? 1500. So 13.26 is RC. 13.26 is RC minus 1
Beta
into 0.05 plus 1. I'm getting 1.61.
1.61.
Correct.
1.
Yeah. So beta is there, RC is there. Can you calculate?
Efficiency around 60.54%. 60.605.
Yeah. So hopefully you will get 60.50. I'm leaving it to you. I think this is very simple. Once you have beta and RC, you can calculate that. Okay. Now coming to the last question. In an engine working on a diesel cycle, the inlet pressure and the temperatures are 1 bar and 17 degrees Celsius. So P1 is given as 1 bar, which is 100 kilopascal. T1 is given 290 Kelvin. Pressure at the end of the adiabatic compression, that is P2, is given 35 bar, 35 kilopascal. The ratio of expansion, that is the after constant pressure heat addition, is 5. So it is nothing but V5 by, sorry, V4 by, no, V5. V5 is the highest. So V5 by V4 is 5, it is given. What is it? It is RE. Calculate the heat addition. Now,
Sir, this is only a diesel cycle. V5, whether it comes, sir.
sorry.
So,
Okay,
V.
okay, okay. I got it. Sorry, sorry. Okay, I will just do it. So 1, 2, 3, 4. So it is V4 by V3. Correct? Am I right? Yeah. Yeah. So we have already developed this equation, the relation between beta, RC and RE. What is that relation?
Expansion ratio, which is equal to compression ratio divided by cutoff
Beta.
ratio.
So what is the compression ratio? What is the compression ratio? It is
That is we
35
need to
by 1, 35 by 1 to the power 1 by gamma. So 35 to the power 1 divided by 30. I think 12.67 I'm getting.
Yes, sir.
So 12.67 by beta is equal to 5. So beta is equal to 12.67 by 5, 2.53. You will get as beta. Now once that is done, heat addition, you can calculate this Cp T3 minus T2. You have all the values like T2 you can calculate from the RC, from the compression ratio. T3 you can calculate by the constant pressure thing is given, no, that you can calculate by that T3, and the expansion ratio 5 is given, so based on that T4 you can also find out. Okay. And once all the values are found out, heat addition is this, heat rejection is CVT3 T4 minus T1, and the efficiency of course you can calculate now itself. So QS minus Q rejected by QS, or whatever formula we have. Okay, did you understand this question? I think this type of question we already done, just value difference
Yes,
in
sir.
the difference in the given, maybe the change in the what are the given is changed, so based on that you can find out. Okay, so that's all about today. So today we already summarized what are the things that was taught in this week 4, and after that we solved the numerical based on Otto cycle, diesel cycle, and dual cycle. So I hope it's clear to you. So we'll meet in the next class next Tuesday. And as you have already sent your some of your queries, I will surely try to submit your answers by tomorrow evening. Okay. So
Thank
if
you
you have
very much, sir.
any,
Thank you, sir.
if you have any doubt for this week, you can also send the mail. I will be answering it shortly. Okay.
Thank you very much, sir.
Okay.
Thank you, sir. Kind of
So
you,
have
sir.
a good evening. Bye.
Yes. Have a nice day, sir. Thank you, sir. Thank you, sir.
Yes.